In our next example, we're going to look at rational polynomials in pi. So instead of integral polynomials, our coefficients are now rational numbers. And I'm not sure if it's a sin to use p and pi in the same way as I've done here, but nevertheless, it's already been done. So this is what elements of q adjoin pi look like. They look like rational number plus linear term plus quadratic term all the way up to some degree. Okay? So this is very similar to the previous example, right? Very similar. Let's just go back briefly. The only difference is instead of being in Z, things are in Q. So this fixes an issue here. Namely, it fixes the issue of 2 not having a multiplicative inverse. We now have that. However, we have a different problem here. So let me write the claim first. So Q adjoin pi is a subring, but not subfield of C. So somehow it's still not a subfield of C, and I will explain why to you. Let's go over the proof that it's a subring. It's a subring by the subring test. And you copy the previous example. So let's go back to the previous example real quick. All right, that's still a rational. This is still an element of our set, so that's good. This just used the fact that the difference of elements stays in the set. That's true for rational numbers. So it's still going to be closed under subtraction. And it's certainly still going to be closed under multiplication because you just get products and sums of rational numbers. So there's nothing different. Instead of the coefficients being in Z, they're now in Q. Proof is the same. Okay? So forgive me, but I'm not going to copy that down. I'll let you do that. It's exactly the same as the previous example. So why is it not a subfield? It's not a subfield because pi inverse, which is 1 over pi, is not in Q adjoin pi. That is, there's no polynomial expression in pi that will give you 1 over pi. All right? So suppose there was. So suppose 1 over pi for a contradiction. And suppose 1 over pi looks like some p0. Again, I don't know. I think I'm committing a sin using p's and pi's, but whatever. Such is life. Suppose that's true, and let's just call the right-hand side f of pi, because I don't want to write that over and over again. So f of pi is a polynomial in pi, and it's equal to 1 over pi. So what this tells us then, by multiplying both sides by pi, is that 1 is pi times f of pi, or equivalently, pi f of pi minus 1 is 0. But f is certainly non-zero, so pi times f is non-zero. And so this expression, pi times f of pi minus 1, this is a non-zero polynomial expression in pi. Well, let me say that better. I didn't quite say that right. Let me just notice that f of x minus 1 is not the zero polynomial. Because f has degree, f is at least a constant. It's not a constant, but it's at least a constant. And so the degree of x times f of x is at least 1. If I subtract 1 from that, we can't create 0 somehow. So x times f of x minus 1 is a non-zero polynomial, and it has pi as a 0. This is impossible. Red, blue, all sorts of colors, contradiction. Okay? Pi satisfies no polynomials, no non-zero polynomials. So we have a contradiction, so therefore 1 over pi is not in this set. So it's still not a field. However, there is a fix, and we'll do that fix in the next example.